All right. Atif, you're up.
Okay, perfect. So once again, thanks, Matt, for this opportunity. Thanks to everybody here in this course, all the students who are joining right now and who will be seeing this recording afterwards. Little introduction. So myself, my name is Atif Khan. I've been here at the company in Sandvik and Alatra since 2009. I've got a computer science background, currently in the area of innovation and university academia collaboration. My background has been in automation and robotics. And with me is Nitendra.
Hello, everyone. Very nice to see you all. My name is Nitendra Mishra. I'm with Sandvik for about 12 years now. I'm working at this time in the capacity of chief engineer for new product development. And I'm a University of Florida graduate from Mechanical and Aerospace MA. I graduated in 2014 with my master's degree. I'm glad to be talking to you here.
All right. So I'll just spend a few minutes just on our company a little bit. So first of all, we always start with safety first. So recently I was on a trip in Indonesia, and it's a good reminder on the back door of my hotel room was a reminder for in case of an earthquake, you're supposed to do this and that, right? Go under a table or under some sort of a secure area like a table, or where if there are any item that falls over, at least you're protected. So it's a good reminder. Like, we're in the state of Florida right now, hurricane season has started. So wherever you are, just make sure that you are in a room. If there's nothing. I don't think there's anything in the scope for today or the next week or so as far as hurricanes are concerned. But just know where your shelter points are, so you're always in a safe spot. So basically, Sandvik itself, Nitendra and myself, we belong in one of the divisions within Sandvik, which is in Sandvik Mining. And within mining, we have a few different areas. Obviously we have mining, we have Sandvik Rock Processing Solutions, and then we have Sandvik Machining and Intelligent Manufacturing Solutions. So we're in the business area of mining, which is actually the most profitable business and the largest business area within the company. 51% of our share of revenue from 2024 comes from mining, and then our machining and intelligent machine manufacturing accounts for 40%. And basically, just like in a nutshell, what this constitutes for is mining is basically we're the original equipment manufacturer for all the different mining equipment that goes in a surface as well as underground mine. So from drills, surface and underground drills, to conveyors, to load and haul equipment on the underground side. We do not have any load and haul on the surface side. That's mostly by our competitors. Rock processing is basically, just as the name suggests, is processing as rocks in the mine, where once our drill machines, they drill and they blast, then it goes into these type of equipment, which you're seeing in the middle, and they basically process the larger rocks into smaller size, which then can be processed for whatever element that they're mining for. And on the right-hand side, the machining and intelligent machine manufacturing, that is basically milling and developing alloys and developing different type of products for like the medical field, like wires that are used in the medical field to like inserting different balloons or stents within the human body to get rid of clots, as an example. So those are some of the wires that we make right here in Palm Harbor, Florida, actually. So beyond that, this one just talks a little bit about our company as a whole. Close to 41 to 42,000 number of employees across 150 different countries. So we truly are a global company, which is really exciting from an innovation perspective, as we hold currently almost more than 8,000 different active patents, which is basically the heart and soul behind any company. So we do spend a lot of time on research and innovation, and basically making sure that whatever we're developing is properly patented. And in some cases, we are also working with universities, just like you guys in the University of Florida, where we're sharing a lot of these items with with academia so that we can, the technology that we're developing are for the betterment as well.
So this revenue that you were seeing, that is in SEK, but if you convert that into US dollar, we are talking about roughly $16 billion here.
Yeah. So quite a lot. These are some of our core values: winning together, curiosity, responsibility, customer focus. Winning together is all about not just winning together on projects that we are conducting within the company, within our own teams, but also along with the customer as well, right? So we always try to take our mining customer along with us especially whenever we're doing a completely new concept, a new project from a mining ecosystem perspective. The last thing we want is just develop something in our own little world, thinking that this is going to be important and find out that it's not really. So that is an example of winning together. Curiosity is all about innovation, always asking, why has this been done this way? Why not do it this way? What else can we do? University academia partnership is also very important. Hiring young talent is also very important because then they also bring in the question about why has it always been done this way? Hey, how about trying it this way as well? Responsibility comes down to being responsible not just to our own shareholders within Sandvik, but also from an ecological perspective. We are in the mining business, so we want to make sure that any deals that we're doing with our mining customer are done in a responsible way, anti-bribery, antitrust, those type of things, making sure that our customers are also responsible in leaving the world in a better way than what they received it as. And customer focus is very similar to almost like winning together, where customer focus is, we keep our mining customer in our focus. And a little bit more than that also, a customer doesn't have to be just our mining customer. It could be within departments as well. Like engineering, our customer would be product management. It could be technical sales. It could be production, all of those type of things as well. So always keeping in mind who our customer is and keeping that in focus. And this is just a little history about our rotary drills division here based in Alachua. So Drill Tech, as it was first known as back in 1974. That's when we were founded. We were basically primarily in the business of water wells. And then we basically started off our first mining machine, the D25KS, in 1978. Then a European conglomerate called Tamrock bought Drill Tech because they decided to enter the surface mining business, and Drill Tech was very well known. So we went by the name of Drill Tech Tamrock in 1987. And essentially Sandvik, based in Sweden, they wanted to get into the mining business. So hence Tamrock had a very good reputation based in Finland, and us based in Alachua. So Sandvik bought Tamrock, with which we came under the umbrella of Sandvik in 1998. Then through different acquisitions, like in 2010, we acquired Cubex, which is another line of underground and surface machines, different types of mining machine, but still in mining. And then 2019 is when we seriously started having our whole suite of product line offering, which Nitendra will go in the next slide. But basically, we started launching our 412i, our 416i, and now today we have our whole series of electric run machines as well as our diesel run machines.
All right, so largely our product is meant for drilling holes in the ground, and our leading customers are mining contractors who buy our machines, and they have specific sites and areas where they foresee the minerals being there, and they use our drills to drill the holes. So we have mainly two series of drills that we produce here in our Alachua factory. Our original series, which is the X series. It's a little, I would say, less sophisticated machine, but it still does the job, and relatively less expensive, more rugged, and known for a long time to deliver the, very high efficiency and very high performance. As of today, our flagship series is the I series, wherein we have a model starting from DR410IE all the way up to DR416I. All these machines are having different capabilities in terms of pull down, which is like the thrust you can put against the ground to drill the holes, as well as the size of the hole, like starting all the way from, let's say, 6 inches in diameter to the 16-inch in diameter, and various hole depths. So our flagship series is also highly automatic, and it has a very sophisticated control system where you can achieve most of the functions with a relatively a huge autonomy, wherein you can probably, not probably, you can certainly operate these machines by using a like a toy pretty much, using some joysticks. You're sitting in your computer room and you can operate machines which might be thousands of miles away. You have very, high resolution cameras to look around so that you could operate them in a safe manner. Like I was saying, we have a very huge amount of digital offering on our machines, on our new I-series machines, and some of the key architecture on our information sharing is shown in this slide. So as you see here, we have our surface drills, and they normally communicate to basically a cloud system which you see. We call it My Sandvik, and through My Sandvik, we have a communication through remote monitoring services that are available on demand, where you can do some preventive maintenance, you can observe the signals of the machine, and then you can take the right decisions. We also have Driller's Office, as you see, which is kind of a suite available for the customer, where customer can see the machine, process the data, upload their documentation and information on the server, and take the right decisions. We have a navigation system which helps us to drill the holes in a very huge amount of accuracy, pretty much in the range of like 10 centimeters or so.
Yeah.
So we can drill holes. That's our committed range, but we can be even more accurate. We also have a capability to integrate with some third-party interface, where we can have some APIs which can connect to our drill rigs, read the data, and sometimes even communicate with our rig. Auto mine, as you see there, this is our capability where we allow our machine and a few more machines in a fleet system, where you can have one control basically cabin which can control more than one machines, up to 3 machines. And it drives, of course, a huge amount of efficiency and fully autonomous drills, and also adds so much of safety layer, because you're not physically in that zone where you are actually drilling, and is still able to achieve the best of the mining world. Now, I think I'm going to talk about some of the things that you probably are mostly interested in. One of the problem that I have thought about, I will share with you. And this picture that you see, this is one of the actual picture taken from a drone from one of our machine that is in Mongolia and drilling as we speak. The holes that you see here, this is not, by the way, a Photoshop picture. This is like actual picture taken from a drone. And as you see those holes in a specific pattern, so that's the pattern you can upload in our machine remotely or by being physically on the machine. And the machine goes on those specific coordinates and drills the holes of your specification, like this diameter, the specific depth, and so on. And our typical process in a machine, in a mining environment, is that these holes are drilled first as required, and then they are filled with some sort of detonating agents, and remotely the blasting is done so that the all solid ground becomes a relatively softer material, and then that material is further processed to remove ores and eventually the fine metals out of it. So the problem statement for the students is that they have to design a compressor oil cooler. In our machine, we have a compressor, which is basically responsible for producing compressed air, which we store in a tank. And the use of the compressed air is that when we are drilling the holes, of course, you are creating a lot of chips and cutting materials, right, that you will be filling the hole with. So as you keep drilling, you are required to flush that cut material out of the hole. And for that, we use compressed air. So from the center of the drill bit, the compressed air will be coming out and it will be flowing out all these chips and other debris out of the hole. That's what you use the compressed air for. The compressor system that we use, that is the oil flooded rotary compressor. And in that, what you have is it is compressing the air, but in order to keep the lubrication and cooling, we inject the compressor oil, which can sustain very high temperatures and it still provide a good lubrication. And our compressor system works on the oil cooling side in a closed circuit. So basically, we are recirculating the oil through the whole system. And at that point in time, it becomes hot. So in order to reduce the or take out the heat from the oil, you are required to design cooling system. That's where this cooler comes into play. So the example that you see here on screen is a compressor oil cooler. You will be flowing in the hot oil from the top of the cooler, and you will be getting the cold oil from the bottom of the cooler. Typically, the size that we are talking about is 100 gallons per minute flow rate, and we use a 2-inch tubing or hosing to deliver that oil to the cooler. The system that it runs at is in the range of maximum 500 psi. So of course you have to have the components such that they can handle that much pressure. And now comes the portion of how do you cool it. So of course it's more of a heat exchanger design where one fluid is flowing through the cores and other fluid, which is the air basically here. We are flowing that through the pins and with the help of a fan, which is basically sucking the air, fresh air from the atmosphere, allowing it to go over the heat exchanger tubes and then delivering the hot air outside. So every time, so the air is of course not in a closed loop system. So some of the technical specification for this system are listed here. For example, first question as a heat transfer student, you're going to ask is what is the heat load, which is shown here as 25,000 BTU per minute. That's the heat load for the hot oil. And the flow rate, as I was saying, is 100 gallons per minute. You may be interested in what are the oil properties like density, viscosity, and whatnot. So there are different ISO standards for that. If you look at ISO 32 and Google it, you'll find all the details. The pressure in the system maximum is expected to be 500 psi. Of course, like any equipment, you see our rigs or our machines are subjected to some of the noise, noise production constraints by the customer. And one of the key contributor in producing the noise in our rigs is the fan. So we are required to control how much noise our fan produces. So of course, the blade angle and diameter and things like that come into play. Like I was saying, it's a closed loop system. So oil, flows around and comes back. The maximum temperature that we would like our oil to reach is 265 Fahrenheit. And that's where we have, so our machine is highly kind of what's the best way to say? It's like self-regulating. So the moment it sees any temperatures are going beyond a specific threshold, it shuts down itself. So this 265 is going to be that temperature. We are continuously monitoring the temperature, and the moment, machine sees that temperature, it shuts down so that further damage doesn't happen. And of course, there is the ideal temperature, right? That's the maximum 265 F, but we would always like it to be in the range of 220 F. Someone might ask why 220 F, because there is another reason for that. If you keep it too low, and suddenly you're going to make it very hot, or you are going to have a situation where you have humidity related issues and thermal and gradient and thermal shocks, things like that. The ambient, our machines go to pretty much all over the world. In fact, you would be surprised to know that most of the products that we produce here in Alachua are not sold within the US. They go outside US. So the ambient capabilities or ambient ranges our machines work in are very diverse and very different. They go all the way from minus 40 C to 50, positive 50 C. They can in fact go to Siberian areas where it could be even further lower than minus 40. And they definitely go to regions in Australia where the temperature could be even more than 50 C. The fan speed. So basically, this cooling system here is designed with a air fan. And for that, we want it to operate no more than in 1600 RPM because it also helps in having a lesser noise, lesser power consumption, and a relatively even higher speed fans can be riskier to work with. Then the fan diameter largely coming based on the real estate availability, not nothing more than that. The fan style that we currently use is a suction type. So what that means is that we are sucking the fresh air from the atmosphere and then not blowing it over the heat exchanger fans. Rather, we are allowing the air to pass through those cores first, and then that air gets sucked in by the fan and thrown out again back to the atmosphere. The power consumption becomes one of the key factor here that we would like to limit the power the fan can consume, because the more power it consumes, a bigger prime mover that runs this fan will have to be. And of course, if you have bigger prime mover, you need big real estate, more expensive and things like that. And sometimes if it's hydraulic drive, it could be counterproductive because then you're generating more heat as well. Dimensions. So in our world, we are of course constrained by the dimensions that we do not have the luxury to have everything as big as they need to be. And dimensions also translate into the cost and material and everything. So the dimensions are shown in the next slide. Like I was saying, the flow rate that you need 100 gallons per minute, typically a 2-inch tube or internal diameter I'm talking about, that should be sufficient. So this is our typical, cooling package looks like. These dimensions are given here. The height you see around 59 inches, the width around 32 inches, and or the depth you can say 32 inches, and the width around 52 inches I see here. So these are almost, rough dimensions for you to work with something and come up with a design. A few things I would say that this is something I'm not really sure because you are in undergrad class and this can be a complex problem, honestly, to solve. It's not something where you have a specific one formula that will help you achieve your results. So in my opinion, you only have few days to work with it. It would be more of approach that would help you rather than coming to a complete conclusion. And if you are on the right path and right in coming up with a solution, that alone I think should be something we would be happy with. And I think this is a problem where you have a fan, so fan laws, fan aerodynamics, all those things are a different subject in itself. Then you have, of course, a lot of convection happening here, right? And conduction as well. I am not sure much about radiation here, but I wouldn't worry about how you rotate the fan. I would just leave that alone for now. as far as rotating, spinning the fan is concerned, you can assume something like an electric motor or hydraulic motor and be fine with it. Of course, this can get into the fin design details, fin effectivity, and how do you keep the target temperature? Either you can overcool, undercool, thermal. I'm not sure in this class if you are even going into thermal fatigue, because that can be a different subject in itself. Uh, that's briefly about this problem. I'm sure you may have lots of questions, so feel free to let me know. Or we have a few more sessions, right, coming in where you can always ask more questions if you have.
I guess one thing that just came to my mind also is, do they have to be constricted by just having a fan? Could be some other cooling mechanism?
Yeah, I don't think so. The example here is what we have been doing. But if you have some other idea, feel free. But only so there is a fact, right, that you could achieve this through many means. But you need to be realistic. What could be done in a mine site, which might be in an extremely remote location? What are the availability of those, let's say,
Parts.
specific liquid nitrogen you want to use? What's the cost of it? What's the logistics?
Yeah.
How much is what's the proven technology? Things like that.
Yeah.
But again, like you said, we don't have to restrict too much ourselves with what is being done already. Feel free to come up with something new if you have to.
Yeah, and that's an important point also, just because keep in mind, like the picture which Nitendra just showed earlier of our drill machine in the middle of Mongolia. Basically, there's no Home Depot around, so you can see mountains in the as far as the eyes can see, right? So the reason I asked that question, if you can come up with any other, sure, you can come up with other solutions, but there's nothing around here. So whatever you design must be robust enough that it's gonna last in this environment. And there's going to be a lot of not just heat and cold, but there's going to be a lot of dust, there's going to be rain, there's going to be mud, all of those type of things. And the expectation is that this machine is going to be working 24 hours a day with no stoppages, maybe for a planned maintenance, but that's about it. So keep those things in mind as well. And I guess, Matt, with that's all we had.
Okay, so I've actually got a couple of questions, and then maybe we turn it over to the students to ask. So first question is about the oil cooler that you have now, which is just to sort of give you a sense of where we are in the curriculum. We just finished talking about fins. I still have to post that lecture, but that's where we are. We're moving now from fins to like multidimensional heat transfer. So I could imagine with the students doing a lot of design work on like fins to increase surface area to reject heat. Can you guys I guess I'm not seeing where the oil goes through and gets cooled. So I see the fan.
Yes. Let me explain.
Yeah.
So this port that you see here,
Yep.
this is where the hot oil goes in.
Okay.
And then in this width that you see here, roughly, let's say a feet or so, you have cores, vertical cores, stacked one after the other along this whole width. And those cores have pins on outside of those cores. Basically, we have fins.
Okay.
And then the cold oil comes out from the port that you can barely see here in this, bottom where I have my cursor. Let me also show you. So this is the port that I'm talking about. These two.
Okay. So somewhere.
Go ahead.
So I don't think we can see it in this view, but there's a manifold somewhere that's made up of like finned tubes that run vertically, and the fan blows air over them.
Yes, so basically the construction here is that this is the side on which you have the fan mounted.
Yep.
And if you look behind this fan, there are cores standing. And behind those cores, of course, this is an open atmosphere. So when you spin this fan, it is basically sucking the fresh air from other side of those cores. So what it does is that uh, the fresh air before it gets to the fan, it has to pass through those cores, and those cores have, uh, of course, they are made up of aluminum and then copper in some cases. But so they have the heat transfer capabilities, and those cores also have fins on outside of those, So that's how it becomes more effective.
Okay, so one possibility for the students to work on would be to look at like alternative fin geometries, like tube and fin geometries that might increase heat transfer, because that's something that we've just finished talking about. Um, so that's one possibility. Um, where else would you want like students to focus some of their design brain cycles? Like where do you see there being opportunities to improve?
I think one of there are many, I would say, directions we can take here. One could be controlling the fan, but that's more of really the control system, not so much of the heat transfer. So as far as the heat transfer, I would say that designing of the cooler itself, and how to make it more effective, because right now the cooling system is that some portion of the cooler cores are seeing more heat transfer happening through them,
Yeah,
and some of them are not that effective.
yeah. If you're
So depending on the flow direction, like right now, it's pretty much, you enter here and you come up, something like that. But does it have to be exactly like that? Or can it be in a different way? Can you inject the fluid in, multiple locations and take it out from multiple locations? Or um,
okay.
you can have more than one fan. So why do we have to have, only one fan? You can have a small, maybe, more fans, things like that. But all that could be a project in itself, I'm not sure how much could be done within a matter of days.
Okay, so possibly multiple fans, and then maybe like a more serpentine path. So instead of, I think I heard right that the oil comes in, it separates into a manifold into a series of tubes,
Yes.
and then from the top the tubes reconnect to a manifold and they exit. But you could imagine
Yes.
maybe like a U-shaped tube that goes up, it turns 90 degrees, 180 degrees, and comes down. So it gets
Mhm.
like multiple passes in front of the fan.
Mhm.
As maybe just an alternative, like how many passes is the optimum number of passes
Mhm.
um, to get the heat rejection that you want. And then was the number was accurate to 25,000 BTUs per minute? That's the correct number?
Yes, that looks too much to you, or
Okay. No, I just that's like 440 kilowatts. So that's
that's
um
a lot of heat.
yeah, that's why I'm asking. It just, which might be fine, right? You guys work
Yeah.
at a much larger scale
Yes, yes.
than a lot of the systems that I'm a energy thermal fluids guy, but a lot of the stuff that I've done is very very small, tabletop and smaller. So 400
Yes.
kilowatts is like that's like 20 houses. So
Hmm.
okay, so that's correct.
Yeah.
It's not an extra zero in there.
No, there's not.
Okay,
And
okay.
as you can see, it's a lot, big, huge amount of flow as well, 100 gallons a minute, right? So it's carrying a lot of heat.
Yeah, gotcha. The other thing that I wanted to ask, and this, I'm worried. I've been thinking about this for a while, and I'm like, I'm going to ask them, and they're going to think I'm, kind of, dumb, but I'll ask it anyway. So have you guys ever thought about using the rig, the tower, for passive cooling? It's a huge fin, right, that's exposed to the environment. I've already run some calculations. You can't get all 400 kilowatts, but you can definitely get about 20% of that. And it's totally passive. But I imagine you guys have already thought about that.
So, are you talking about the huge tower which we call mast and using that for
Yep,
some natural convection kind of thing? Like,
exactly.
yes, I mean, I don't think we have honestly thought about it, but we are definitely open to some of these ideas. And even if the chances of adoption would be very low, but it wouldn't hurt. Sometimes these out of box ideas could be very interesting, and you never know, what we may want to adapt. Uh, of course, there will be a lot of restrictions and challenges there, but I wouldn't focus on all those too much right now. Um, we have I mean, the mast is a moving component, really, right? It goes up and down, and there are pipes and other things on it, and then uh, transferring that cold oil from something that's moving, up and down, and having those connections and joints, and bringing it back to a stationary portion. All that may bring some challenges. Uh, but definitely you will get a big benefit of big surface area, right?
Yeah, that was my initial thought. Like I said, I've already run a couple of numbers because I'm like, they must have thought about this already. So, so you,
Another another challenge there is that as I was saying, we send our eggs in extremely cold environment,
yeah,
and where the natural convection becomes an issue because the gelling and freezing, because cold breeze is so heavy there that it's a very tricky design. Really, you do not want, like I said, overcooling as well. So that's
yeah.
why uh, we have to be mindful.
Gotcha. So there's a question from a student in the comments, and I'll just read it for the benefit of the recording. So the question is a thermodynamics approach, for example, a Rankine cycle, or I'll add this, a refrigeration cycle, a possible option?
Uh, I wouldn't discourage from not thinking in that direction. I would say, as far as the practicality is concerned, that is something we can discuss later. But why not think about
I
it,
mean, we have the AC inside the inside the cab for the operator, right? So that
Yes,
requires refrigerant.
yes,
Obviously, this will be a little bit more,
yes.
just a little bit more refrigerant
So as
needed.
long as we keep the power consumption, in that range, and then of course, the cost and other things roughly in that range, then it should be okay. But like I said, like Atif said, we do have a air conditioning system, so we do deal with refrigerant. Of course, not for this purpose,
Mm.
uh, because we are not trying to be extremely cold here, right? If you look at our ideal temperature, that is still pretty high, honestly,
Mm.
right?
Mm.
And the scale at which we are producing heat uh, is huge.
Mm.
So it may be, if, if you run the numbers later, you might realize it might not be a very viable compact solution. But why not?
Yeah,
Think about it.
why not? That
Why
would be
not?
Yeah,
interesting.
something worth looking at. Yeah, yeah. I mean, given the amount of time we've got, the students have like a week. I'm thinking, they probably want to do like a brainstorming session, maybe now, right? Like as soon as the session is over in their groups. But pretty quickly, I would say like by the end of the day today or maybe early tomorrow morning, come up with something that they want to pursue. And then, spend the remainder of the time this week running through the calculations. And I think, you're giving us pretty wide, um, you know, permission to be creative. So I think it's fair to say that even if the students ultimately come up with something that, the numbers say is not viable, you'd still be interested in just seeing the idea and seeing the calculations, right? It's
So the way I see that is, and not to discourage students
Yeah.
as such, but the reality, or the way I see this exercise is more of a thing where students get an opportunity to see the real life problem and they come up with something. I am not so much into getting a perfect solution from them, you know. It's more of a idea that I would look for, because this could be a project of 6 months, you know, and prototyping and trial and things like that. So it was just hard for me to isolate a very specific heat transfer problem, um, uh, 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 mm, because more and more I restrict myself, then I wouldn't be close to the real life, because in real life, there's nothing like a standard textbook problem, right? It's always going to be complex. So I didn't want it to be very truncated and small, so that it could perfectly matches with the timeline that or knowledge that the students have. I wanted it to be real problem, and then give them the freedom to explore and come up what best they can, and you know, go from there.
Sounds good. So we have another question in the chat, which again, for the recording, I'll read. So the question is one of the goals to generate a model to optimize the fan's activity based on the ambient temperature? Because I would think the design would be significantly different if the ambient temperature was -40 as opposed to 50 Celsius.
Yes, so the idea is to not have a different cooler. Definitely, like the hardware side has to remain the same, but as far as the software side, I would say, or control side, that definitely is the variability in that is acceptable, if that was the question. Like you can run no fan to less RPM to high fan depending on the ambient conditions, but it shouldn't be something like you remove half portion of the cooler in cold weather, because that becomes very, that becomes a physical activity.
So once the the design is finalized, I think that, correct me if I'm wrong, but the two things that they can modulate are fan speed and then the oil pump rate, right? And then I guess conceivably they could also, if they had a manifold that had valves on the bottom, they could like activate and deactivate different pathways in the manifold.
Yes, that's definitely possible.
Okay.
As far as the flow production by the compressor, because it's a hard couple with our engine, that's not going to reduce. But you can always have alternative. So since it's a closed loop system, you have choices to either send the whole 100 gallons to the cooler, or only send maybe, I don't know, 50 gallons to the cooler, or no gallons to the cooler. And then you can always bifurcate that and send it back to this closed loop, because the cooling is really necessary if there is a need of cooling, right? If there is not enough heat, then you don't need to send it to the cooling system. It can circle back to the same closed loop system.
Makes sense. Okay. Well, so we have at least by the original schedule, we've got 9 minutes left. So are there any other questions from students?
May I ask one?
Yeah.
I was just wondering, I don't know what like CAD software you guys made this in or if it's modeled in it, but is it possible to get like a cutout view or like an exploded view of like what the current inside slash heat exchange method like currently is, like the piping, like the inner workings of it sort of thing?
I will have to look, because honestly speaking, this cooling package is not something we design. We rely on our suppliers, cooling system suppliers, who do the detailed design for us, and they are the expert in this area. And a lot of time the models they supply to us is more abstract and not super detailed at the lower level. So, but I may be able to get it. I will, if I do get, I will definitely share. And I will also go to our production floor and send you guys some of the real pictures of these cooling systems that may give you a little more clarity or perspective of how exactly they look like.
Yeah, I think
Yeah,
that would
that'd be
help out.
awesome. Thank you.
Yeah, cool. Thank you for the question. So along the same lines, another question in chat. Um, what fin? Let me try again. What fin geometry does the compressor currently use?
So I think it's about the cooler. Probably they're asking, not so much about the compressor, right?
Yeah, I think that's right.
So the pin geometry, as far as I remember, it's not anything super fancy really. It's soldered fin on the main tube, like a 90-degree vertical, fin soldered on the main tube. That's pretty much it.
Okay.
Not like a variable profile. Maybe that's what you guys are studying. I kind of remember my 20 years old days. So it's nothing like that.
Is it helical, or is it just a series of uh, toroids, like donut shaped um, fins?
It's more like you have vertical tube.
Yeah.
Oh, you guys can see me actually, I believe, right? Still?
Yeah, we can. Yeah.
Okay.
If you stop sharing, we can actually see a bigger version of you. Right now, you're a
Oh,
tiny little thumbnail.
There
yes.
you go.
There we
Yes.
go. Yeah.
So I was just going to say that we have like a course, something like this, and then we have like a rectangular, fins attached to welded or soldered to these guys,
Okay.
pretty much all along the length.
Yeah, so much like
So
a heat sink in a CPU processor on a computer.
yeah, something like
Yeah.
that. And they are pretty close. So they are not like far apart. They are really close. So one of the challenge there is also the dust, if whenever machines go to our like these mining areas and all, they are very, of course, dusty areas and the dust accumulation happens. So if you don't keep those clean,
Mm,
less and less effective they become, right? So that's one of the challenge. But I think some of that will become more clear once I get an opportunity to send you guys pictures.
okay. Interesting. Okay. So we've got about 5 minutes left. If there are any other questions from students while we have the engineers here, much easier to ask them now. Nope.
I have one question, Professor, for you. What do you think about the problem? Uh, is it exciting and is it more difficult than you thought, or it's easier, or what's it
It's
in
it's
general?
exciting to me. I'm an energy thermal fluids guy, so this is like right up my alley. So I'm pretty excited. I was actually I was a little worried because initially when I looked at your draft slides, I'm like, oh no, this is a heat exchanger, and we're not there yet, and that's still several weeks in the future. And then when you described it, and it's just an oil cooler, I'm like, okay, we can actually tackle this because its fin design is really the big thing that students are going to have to work through. And we just finished that module, that chat. We literally just like last night. I just finished the last lecture on fin design. So this is like right up our alley, I think, especially if the students can focus in on different fin geometries and fin design. The challenge for us, and so I'm going to have to read ahead in the textbook a little bit, is going to be coming up with the forced convection coefficients. So calculating H values. We're at the stage in the class right now where, in fact, I think I've told a couple of students this in our private interactions in chat. You're sort of at the phase where you have to just trust that the H value that we give you is right because we haven't taught you how to calculate it yet. So I might just do a little switch of like the order in which I was going to do things and just do a quick module on calculating forced convection H, because they're definitely going to need that if they're going to start thinking about different fan velocities. But no, I think everything with the exception of coming up with that H value is definitely within the scope of what the students are able to do right now. So I think it's actually the perfect problem for this point in the semester.
And I would say wherever you have difficulty in finding a specific values for a parameter or anything like that, just assume something, whatever you think is reasonable, and move on. Because I have gone through that route, right, where we get crazy about finding the specific value of that particular variable, and then we spend all of our energy in finding that rather than just thinking about the whole problem holistically. So it's okay to make assumptions um, and move forward, because the overall idea or your solution has more value rather than being that accurate in a specific point, right?
Yeah, they do have this is table table 1.1 in the book is becoming famous. It's the very first table in the book, and they have listed a series of different convection conditions. So natural convection, forced convection, convection with radiation, and they have kind of a range of acceptable values. And the quiz has been submitted, so I can say this now. The answer to the first part of the quiz was the students actually had to go to that table and find the appropriate convection value. So they're familiar with doing that. So I'll probably give them just a quick primer on calculating H in kind of a broad way, but then they can go to that table and they can find for particular forced and natural convection situations, they can find characteristic H values. So we can probably start with that and then have them follow up with a back of the envelope calculation just to confirm that their guess is right, because the range is quite big. It's 25 to I think 250 watts per meter squared Kelvin. So just to get the right order of magnitude, they probably want to do a back of the envelope calculation. But yeah, once they calculate a number, we can focus on the design of the system rather than pinpointing the H value. Good. Okay. Well, this is students. This is your last chance. We've got 1 minute left, and then we're at the end. So, um, any final questions before we wrap up?
You guys don't, I'm assuming since the system was like a third party system, you guys don't know the manufacturer of the fan, right? I mean, I don't know if this is common, but I would assume that they might have an H value on like their website or something.
Yeah, so you can go to a fan supplier called Multi-Wing, Multiwing, and there is another company called Horton, Horton, and we use fans from both of those companies. And if we don't use, our suppliers use them, so I do interact with them. You
Okay,
might
thank
be
you.
look for the range in the range of 54-inch, 60-inch diameter, something like that. You will find some good details there.
Okay. Well, we've reached 3 o'clock, so that's the official end of the session. So I want to thank you guys for spending the afternoon with us and giving us this presentation and this really interesting project. Like I said, I'm thrilled. I'm an energy thermal fluids guy, so this is like right up my alley. I love doing this kind of work. In a way, this mirrors. So 1,000 years ago, when I was an undergrad, I did a year abroad at the University of Bristol, and we had a very similar it had nothing to do with mining, but we were designing a heat exchanger, and it was a very similar format. And I always thought that that was like the best week of my entire undergrad life, and I've been looking for a way to reproduce it at University of Florida. So I'm excited that we're able to do this in this format and give the students a real world open-ended problem to solve in the context of a heat transfer class. It's right now we're just solving problems, and they all have answers in the back of the book. And so this is I think a very good opportunity for them to see kind of what the real world is like in terms of there's no limitations, right? Any good solution should be on the table and should be considered. So appreciate you guys being the pioneers on this, be the first ones to go through the gauntlet. And we'll, like I said, see students' response and adjust accordingly. But love to continue doing this in follow-on semesters.
Absolutely, we'll do, and maybe in live as well, right? In person on
Oh
campus.
yeah. It'll be a much different different interaction when you have 160 some odd students in a live lecture hall than
Right.
doing it asynchronously online for sure.
Cool. Thank you. Thanks for the opportunity.
Great. It was good talking to you, Professor, and lots of good questions. And mm, I would say enjoy the problem.
Yeah, thank you.
Thank you.
All right, very good. Well, we'll stop the recording. If I can find how to do that. There we go.